In this video, we want to extend and make more precise some of the definitions that we made in the previous video. Our experience with the world lines of particles that do not have a uniform motion has shown us that it is convenient sometimes to go to non-inertial reference frames. Those would be reference frames, for instance, that are co-moving with a particle in non-uniform motion. However, this is difficult to accommodate with the formalism that we have developed so far, and we need to introduce more mathematical machinery. So in this discussion, we are going to work in some space-time. Okay, for the moment generic, let's not mention the metric for the moment. And this space-time, at least in some region, will be equipped with some reference frame with coordinates x mu, which are completely generic. They don't have to be Cartesian anymore. We will have another coordinate system in the same region that we will denote by x mu prime. And of course there will be some relation between them, so we can express the x mu primes as functions of these coordinates x's, and of course it is always possible to find the inverse relation. These changes of coordinates have associated a Jacobian matrix. Okay, this is a matrix that we can write G as G mu nu, and that we are going to assume always, which is non-singular. Basically, this means that we can invert this change of coordinates that is invertible. So now with this setup, we can define again, if you want, in a more precise way, because we didn't give a very precise definition before. We just treated the vectors as a set of numbers labeled by the index mu. What a vector is at a point P. Of course, a point is an event in space-time, and this kind of vector is also called a contravariant vector. Okay, so it is an object, a mathematical object, a geometrical object, which is characterized in the coordinate system x mu by 4 quantities that we denote by v mu p, which are called the components of the vector in the reference frame x mu. And the property that defines, that tells you that these components are the components of a vector, is that when I go from x mu to x prime mu to this new reference frame or coordinate system, these components also change, and they change in a very precise way. So the change is this. You take the Jacobian matrix evaluated at the point P, and you multiply it by the components V mu P. This is, if you want that, we can write this as G mu nu evaluated at P times V mu P. Okay, this is a contravariant transformation law, in the sense that we can, if we write this as a column vector with our conventions, okay, this is a matrix, and this is the original vector, and we call this a contravariant transformation law, and something that transforms in this way is a contravariant vector. So now we need the example, and the main example of a contravariant vector at a point is given by the tangent vector of a world line that passes by the point P. So suppose that we have the point P, and there is some word line. We don't care if it is time-like or whatever. This word line is parameterized by some parameter lambda, and for some value of this parameter lambda p, okay, you get precisely the coordinates of the point P. Then we can take the derivative of x mu with respect to lambda and evaluate it at this value lambda p, and this is a tangent vector to the word line at this point P. Now, does it satisfy this definition of contravariant vector? Well, we just have to express this in the coordinate system, the primed coordinate system, and apply or use the chain rule. So the chain rule tells us that this is going to be this. Okay, so in fact this will be the derivatives. Okay, this will be evaluated at the point P, and this will be evaluated at lambda p, and this is exactly the definition that this fits exactly the definition of contravariant vector that we have found. Okay, so this is the main example. There is also a main counterexample, which are the coordinates x mu themselves, which often in elementary texts of special relativity they are treated as vectors. However, for instance, under a Poincare transformation, we know that these x mu's transform in this way. Okay, I can compute the Jacobian matrix, and it is just lambda mu nu. So this is the Jacobian matrix. It is constant, so I don't need to write P because it is the same everywhere. Okay, so you see that the transformation rule of x mu has a piece which is right, which is correct, as the transformation rule of a vector, but there is this inhomogeneous term which never appears in the transformation law of a contravariant vector, in the definition of a contravariant vector. So the x mu's are not vectors. Okay, another example that of something that transforms as a vector, okay, is these differentials, because according to the chain rule they transform in this way, but it is not so easy to evaluate them. Okay, you have to say that they are defined somehow at the point P. Okay, and this is the infinitesimal version of this delta x mu's that we used in the previous video as an elementary concept of vector, which was good enough for Minkowski spacetime, but it's not good enough if we consider another spacetime with a different metric, or maybe complicate the coordinate systems. So the second definition that we are going to make is that of a differential form. At the point P. Okay, this is another geometrical object, and for the moment we are just defining these objects at a given point in space-time, not everywhere. These differential forms are also called covariant vectors. And again, they are defined by their components in some coordinate system x mu, and we say that these components are omega p mu. So let's write this p above to avoid confusions, because the index in this case comes down. So we say that these components, again, these are four components. We could arrange them in a column or row vector, but by convention something with lower indices will always be represented by a row vector. And then we say that these are the components of a differential form or of a covariant vector if when we go from x mu to x prime mu, these components change in this way. So we have p prime mu is omega nu p x prime mu evaluated at p. Okay, this is, or these are the components of the inverse Jacobian matrix evaluated at p. You can check that this is the inverse Jacobian matrix just by multiplying one by the other, and you will find that the one by times the other is just delta mu nu. Okay, so this transformation rule we would express in this way. Okay, as a row vector, another row vector multiplying by the left a matrix, and if in this case the matrix is J, okay, in this case this matrix is J minus 1. This is contravariant law of transformation, and this is the covariant law of transformation. Okay, so which kind of examples we can find? So suppose that you have a function f of x, and that you consider the partial derivatives of this function x mu at the point P. Let's see how this object of these four numbers, in the end these are four numbers, when we take the partial derivatives and we evaluate them at the point P, so how they transform if we are in the prime reference frame. Of course the P, I don't need to write P prime, the point is exactly the same, it's just the coordinates that take different values. When it is a different coordinate system, the coordinates of that point are different, but the point is the same. So we again apply the chain rule. Sorry, this is f, and this is x nu. This we have to evaluate p, and at p. Of course, this is just a set of numbers, so the fact that I write them in one order or the other doesn't really matter. So it fits the definition of differential forms. Having these definitions, we will assume from now on that any object that has an upper index is a vector. It's a contravariant vector, but we call it just a vector. And any object with a lower index will transform as a differential form. And the only exception to this rule, or one of the few exceptions, will be the coordinates that have an upper index and don't transform neither as a vector nor as a differential form. Okay, the first thing that you can, the first property that you can find is that if you have a vector and a one form and contract, this is usually called contraction, the fact that you multiply two of these objects and with a repeated index, so there is a sum here. So this B0 plus A1, B1, etc. The main property is that so these are defined at a point P for the moment, is that if you go to the prime coordinate system, Then by definition this transforms as x prime mu dx nu, always at point P, and this transforms as dx rho dx prime mu at the point P times b rho. Okay, we could have written also j mu nu a nu at point P and b rho g minus 1 rho mu at point P. Okay, the order doesn't really matter. What matters is that the product of these two things, okay, j and j inverse, and it is a product because they are multiplied by they have this contraction in mu, so maybe the order, just to make it more explicit, to see it more easily, you would write it like this. So if you contract the second order, the second index with the first index, this is the standard matrix multiplication, okay, rows times columns and so on. This by definition of inverse gives you delta rho nu, and if this gives you delta rho nu, a nu b rho delta rho nu, anything multiplied by delta is just the same object but with this new index nu. So what you find is that the expression, this is an invariant. It takes exactly the same value. Invariant and scalar is the same thing. And invariant doesn't mean that this function, because in the end is the same as a function, has exactly the same functional form, because probably you want this to be expressed in terms of the coordinates x prime and this in terms of the coordinates x. So in order to compare, you have to perform this coordinate transformation. So you express this in terms of x and this in terms of x, and then it takes the same form. Okay, but in different coordinates, the expression will be different. The value at that given point will be exactly the same. Okay, and in any case, this is going to be evaluated at point P. One of the problems with the transformation laws of vectors and differential forms is that they are sometimes difficult to remember. Where is the prime here or here? Okay, so there is a notation which is particularly good because it will make us remember always what is the right transformation rule. So if I have the components of a vector at the point P, I write this expression okay, where it is assumed that I'm going to evaluate this partial derivative at point P. Okay, so this is an association between what I have called a vector of the components of a vector and a differential operator, something that operates, for instance, on functions and gives you another function. Okay. The difference is that these are components. They will be different in each coordinate system, while this operator is really an intrinsic object. It is something independent on coordinates. So if I am in a prime coordinate system, so these are the prime components, by definition of the covariant transformation law, this is x mu prime dx nu, and using the chain rule, all this should be evaluated at P and then partial x rho. But this is j mu nu evaluated at P, and this is j minus 1 mu rho. And to see that this is contracted in the right order. So this is going to give you delta rho nu, and this gives you nu p partial, okay, this evaluated at p, x nu also evaluated at p, so which is what we defined as psi p. So this object has the same value in any coordinate system. It is an intrinsic object. If I don't remember how psi transforms, I will get it from this expression. So if I have psi p and I know that it is the same in any coordinate system, so if I start with this expression in this primed coordinate system, I just apply the chain rule to the partial derivative, and this is the transformation law. It looks different because here this is the inverse relation, if you want, psi mu and psi mu prime. If I do it without primes, then the prime would be here, and this would be psi mu prime. You don't need to remember all the details of the transformations. You just need to apply the chain rule to this operator. For differential forms, there is an analogous, I don't know what to call it, trick. So to these components, you associate an object that you just denote by omega p, and you write in this way. Okay, again, if I don't know how this transforms, suppose that I just have to remember that by definition this is going to be an intrinsic object, so this should have the same expression in the prime coordinate system. So if I use the chain rule, okay, everything evaluated at p, then you see that this is exactly the same definition, I mean, this transformation that appears in the definition of differential form. The only difference is that I have used different indices, but as you know, the indices, the particular names of the indices do not really matter. So it is really convenient to use this expression for differential forms and this expression for contravariant vectors. Now that we have defined these fundamental geometrical objects, we can define more general objects that we call tensors. First, a tensor of rank r, s at the point P, okay, is an object whose components, the components in the coordinate system x mu. So we have this coordinate system, and these components are defined in that particular coordinate system, and these components have r indices of this kind and s indices of this kind. So r contravariant indices and s covariant indices. So what does this mean? It means that if you go to the prime coordinate system, this object will transform in this way, and I have to write this here because new one, new s. Now I have as many factors of this kind as contravariant indices, so all these factors are Jacobian matrices evaluated at P, and I have R of these indices, then I have R factors like this, And okay, we can write this already. And I also have S factors, in which it is the inverse Jacobian matrix that appears. So it is x sigma 1 dx. So originally it was nu 1 evaluated at p, and dx sigma s dx nu s evaluated at p. So this would be the general transformation law of a rank r, s tensor at the point p. Rank r, s, or r times contravariant and s times covariant. Okay, so we have already met our tensor of rank 2, 0, which is the metric tensor. Okay, it is an object that we have written like this. Okay, writing mu1 or mu2 would not make any difference. I can also write rho sigma or whatever. Okay, it doesn't. These are just labels to, for the components, and what matters is that when you go from x to x prime, this object transforms in this way. Beta, sorry, the primes are here, x sigma prime. Okay, and is always evaluated at p. We can use this trick that I showed you before to remember how this object always transforms. So this is rank 2, 0, 2. So it's 0 times contravariant and 2 times covariant. So one would write something like this, because automatically, if you want to relate the expression of this object in prime and unprimed coordinates, so let's say that you start with the unprimed ones and you just apply the chain rule. Prime dx nu dx beta prime dx alpha dx beta. If you compare with this expression, apart from the fact that you have to evaluate everything at the point p for the moment, okay, the difference is that they have used this mu and alpha and so on in exactly the opposite places, but nothing forbids us from changing mu by alpha and nu by beta. It's exactly the same thing. Okay, and this object, okay, for the reasons that we have explained more or less, this is usually denoted by ds square. This is the space-time interval, and if you divide both sides by ds square or ds, what you find is that this is mu ds, dx nu ds, so s is the proper time, but more than the proper time or proper space, this is the invariant interval. Remember that one of the interpretations or one of the properties of the proper time is that it is equivalent to the interval along this word line, if this is a word line. But in general, we just write this thing, okay, dx squared, so this. Okay, with the metric tensor we can construct that we have A metric tensor provides us with a scalar product between vectors, contravariant vectors, at a given point. So if you have two vectors, psi and z, okay, by definition, this scalar product would be psi mu, psi nu, g mu nu. And we know that this is symmetric, and it is not positively definite in space-time. Of course, you can always change and use a metric that has all pluses or things like that, but in principle this doesn't really matter. Another property is that, okay, and again I should write p everywhere. Another property of this of the metric is that it can establish correspondence between contravariant vectors and forms. Okay, so these are the components of a contravariant vector at the point P, and these are the components of an associated one form at the point P. I use the same symbol. I could use a different symbol, but conventionally, and for the fact that because of the fact that it is in a one-to-one relation to this contravariant vector, we use just the same symbol, and this is computed in this way. If the metric is invertible, and we always assume that one of the assumptions is that the metric may not be positively definite, but the metric should be invertible, then we can perform do the inverse operation and associate a vector to any one form, and it could be the same vector. Okay, so how do we do this? Just we have to explain the notation. So the components of the inverse metric are usually denoted by upper indices. Okay, and this is natural because they transform contravariantly when the components of the standard metric transform covariantly. Okay, they are defined by this property. Okay, and also in the reverse order. And by convention, and because, as I said, theoretical physicists are lazy people, we suppress this -1 in parentheses, so g -1 mu nu. The components of the inverse metric are represented by just g mu nu. When you see up, g with indices up, it refers to the inverse metric, which we assume always that exists. So now if I have, suppose that I have this same differential form, or the components of a differential form, then I can associate to it this contravariant vector, which is defined by mu nu psi nu p. Now if this was the one form that I associated before to this vector, you see that the whole thing matches perfectly because this is nothing but this. Okay, and this is delta mu rho psi rho p, and this is just mu p. So things match perfectly well. Okay, this operation of associating one form to one vector and vice versa is called lowering the index or raising the index, and it is understood that basically it is the same object, or it contains the same fundamental information, but it is represented in two different forms. This is why we just say that it is some object that we call psi, and we raise or lower the index on that object. Finally, we have made all these definitions of vectors, forms, and general tensors at the point P, and we just generalized them to fields, so vector fields, one-form fields, and tensor fields in general, so they satisfy the same properties at any given point. Okay, so basically a tensor vector field is, as any field, is an assignment of a vector to each point in space-time. This is given instead of by 4 numbers, it will be given by 4 functions. These are automatically is understood that this is in the unprimed reference frame. So if you go to the primed reference frame, what you find are 4 functions, and these 4 functions are computed according to the covariant transformation rule. But now this Jacobian matrix is not restricted to a given point, but it takes all the possible values. And what you have to do, okay, in order to find these quantities as functions of x prime, is to express the coordinates x as functions of x prime here. Otherwise you get still functions of x, and you would have to do something. Okay, and the same goes for one forms. So we get one form fields that transform in this form. So it could be x of x prime again, x nu, and x prime mu. Okay, and now not restricted to the point P, and so you don't need all the examples. I mean, the tensors transform in exactly the same way. In special relativity, we are only going to consider the Minkowski metric, but we will express it in different coordinates. Okay, we know that in Cartesian coordinates, this is the Minkowski metric. In Cartesian coordinates, it takes the form ds square. This is the standard notation ds square, and this is just d square minus dxi, as we know, where c is equal to 1. We have also used or defined like-on coordinates. And in these coordinates, the same metric, as we saw, takes the form 2 du dv minus dy squared, or x2 squared, minus dc squared. Okay, we have already combined the values of eta that we found with these differentials, and instead of, well, this could be x plus and x minus, but this is the form of the Minkowski metric in like-on coordinates, where I have combined t and x, or t and x1. Finally, we have spherical coordinates. Okay, in these coordinates, nothing is done to the time, to the original time coordinate, but these quantities, these spatial coordinates, are expressed in terms of angles. These are my definitions of for the spherical coordinates. So x1 is r sine theta sine phi, x2 is r sine theta cosine phi, and x3 is r cosine theta. Okay, there are in the literature, unfortunately, different definitions, slightly different definitions for spherical coordinates that differ. Some signs are changed by cosines and so on. This is the one I am taking. Okay, so how do I change from dxi to dr, d theta, and d phi? Okay, I could compute this matrix, this Jacobian matrix, okay, for with all the dxi's and then dr, dxi, d theta, dxi, d phi, and so on. I have to multiply the metric 2 times by this inverse Jacobian matrix, so this is too complicated. Instead of this, I just apply the chain rule. So how do I do it? I just differentiate here. So this would be, okay, first I take the partial differential with respect to r, so I get sine theta sine phi dr, then plus the partial derivative with respect to theta, so it is plus cosine theta sine phi differential theta plus r sine theta cosine phi d phi. I do the same for dx2, so I get similar expressions, sine theta cosine phi dr plus r cosine theta cosine phi d theta minus r sine theta sine phi d phi, and the x3 is cosine theta dr minus sine theta d theta, and nothing else. Okay, then I just replace dx1, dx2, and dx3 I have in this expression. So I have to compute dx1 squared, dx2 squared, dx3 squared, and then I have to add all of them. If you do this calculation, which I advise you to do as an exercise, what you should find is minus dr squared minus r squared d theta squared plus sine squared theta d phi squared. Okay, this is often written as d omega squared for reasons that I will explain you later. Okay, just as an exercise, if you are given this form of the metric, you can find the components of g mu nu in these coordinates. So now the coordinate t, the coordinates are t, r, theta, and phi. And you see that this metric is diagonal, only the squares of these differentials appear, there are no cross terms, d theta, d phi, so this is really easy to do. So this is 1, this is minus 1, minus r squared, and minus r squared sine squared theta. These are the components of the metric, of the Minkowski metric in spherical coordinates. If we had tried to find the form of the Poincare transformations by imposing the invariance, the form invariance of the metric in spherical coordinates, we would have found, first of all, it would have been much more difficult, and we would have found very complicated expressions, more difficult to understand. So for that particular problem, Cartesian coordinates are very, very convenient. For other problems, however, spherical coordinates are much more convenient. So for instance, for things that rotate, for spherically symmetric situations and so on, as you know very well. So this is why we need to know how to deal with all of them, even if we are using only the Minkowski metric for the time being. We are not going to introduce more mathematical concepts for the moment, but these definitions that we have made of vector fields, differential form fields, and tensor fields, very often we will not say fields, it will be understood, and then these definitions are valid in much more general cases and for any metric, so you have to learn how to deal with them. Okay, and this is the end of this part.